Hello, good evening. 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 Oh, I see three viewers. Hello, guys. Good evening. It's 30 seconds and we will start. I have promised you previous time that I will show you some talk from Jack Shirazi, from the guy who has created this Java performance and tuning newsletter. I lied. I have found another talk which kind of interesting for me, but also I guess it will be interesting for everyone. I hope so. About JIT optimizations and about runtime optimizations, and it's a little bit special because I actually was looking for the talk from about JIT, and found that the guy who actually introduced me to the topic of low latency and about this, like all this low level stuff, I was working at that time at Luxoft. It was not a big experience. I moved to Krakow for that for half a year, and I wouldn't say that it was a big success, but I had a amazing training about low latency, and this guy was actually doing this training live. Yeah, so I was with him in the same room. He like shared with us a virtual machine with like prepared tasks, etc., and it was like 3 days, 3 full days of training. So I will show you his talk, which he was doing at Vox Days in Vienna. This will be second part of our stream, and the first part is usually JVM anatomy quarks, and here I also have a small introduction. I'm actually walking my dogs with one of our viewers, and we had a discussion about previous talk about previous article about TLAB allocation, and we were discussing, and I realized that I also don't understand quite a lot of things from these TLAB allocations, and the next article actually answers some of those questions. So let's start. TLABs and heap parsability. Let's switch it on. And question: have you ever encountered the large int arrays that cannot be accounted for? Those that are seemingly allocated nowhere but still consuming heap. Those that have some garbage looking data in them. I actually didn't encounter, but I guess someone who was analyzing the heaps, they could see it. And let's read about the theory behind that. In GC theory, there is an important property that good collectors try to maintain: heap parsability. First time when I was reading this article, I've heard about heap parsability, never heard about it before. That is shaping the heap in such a way it could be parsed for objects, fields, etc. without complicated metadata supporting it. In OpenJDK, for example, many introspection tasks walk the heap with a simple loop like this. And I suppose that this is C code, yes, so they take the cursor and put it on the heap start. Yeah, then while cursor is less than heap used, it takes the object Yeah, put they take the object under the cursor, then do something that they need to do with the object, and then move the cursor to size of the, let's say they take the size of the object and move, like the cursor just jumps. Yeah, so quite simple operation, that's it. If heap is parsable, then we can assume there is a contiguous stream of object from start to the allocated end. This is not, strictly speaking, a required property, but it makes GC implementation, testing, and debugging much easier. So, if we don't have gaps, yeah, so if we have a gap, then actually the JVM will not know at which point it needs to move the cursor. Yeah, if it has the object, it just takes the size of the object, yeah, and move the cursor appropriately. Enter thread local allocation TLAB machinery. This is previous article which we were looking previous time. Now each thread has its own TLAB it can currently allocate to. So let's remember what is TLAB. Yeah, this is each thread which starts in JVM. Yeah, it immediately allocates some buffer where he puts the objects. Yeah, it makes like allocation much cheaper. Yeah, so that it doesn't go to some memory allocator of operating system and to JVM, like how it managed. So it allocates immediately quite a big size of the heap. From the GC perspective, this means the entire TLAB is claimed. So from GC perspective, looks like this TLAB is fully occupied. Yeah, GC cannot easily know what threads are up to there. Are they in the middle of bumping the TLAB cursor? What is the value for TLAB cursor anyway? It is possible that the thread just keeps it somewhere in the register, in OpenJDK it is not, and never show it to external observers. So there is a problem. Outsiders do not know what exactly happens in TLABs. So only thread which allocated this TLAB knows what is going on there. Yeah. We might want to stop the threads to avoid their TLAB mutation, and then traverse the heap accurately, checking if what we are walking right now is the part of some TLAB. But there is a more convenient trick. Why don't we make heap parsable by inserting filler objects? That is, if we have, and actually one of the questions which we were like discussing with the viewer, with River actually during our walk with the dogs, is does like how GC does it stops the world while it's traversing the TLABs, and looks like yes. Yeah, so we might want to stop the threads to avoid the TLAB mutation, and then only then it traverses the whole tree of objects, yeah, which were created, and actually it traverses, looks like it just traverses the whole heap. And then why those fillers are needed? Yeah, so there is one TLAB, let's imagine, then there will be next TLAB, etc. And some part of TLAB is not used. Yeah, so we have here a used part of TLAB, and then we have not used part of TLAB. And this TLAB, we like what he's writing here. Why don't we make heap parsable by inserting filler objects? Yeah, we can stop the threads and ask them to allocate a dummy object in the rest of TLAB to make the part of heap parsable. Yeah, so it allocates here the object, one object, yeah, and it knows now why it makes the heap parsable. It can define actually the size of this object, and it will be parsable. What is a good candidate for a dummy object? Of course, something that has variable length. Why not int array? Know that putting the object like this only amounts to putting out the array header. and letting heap mechanics to work out the rest, jumping over its content. Once thread resumes allocating in TLAB, it can just overwrite whatever filler we allocated, like nothing happened. The same thing, by the way, simplifies sweeping the heap. If we remove sweep out the object, it is convenient to place a filler in its place to keep heap walking routines happy. Here again, a little not clear for me question. If we are speaking that garbage collector is not removing the objects, yeah, it's copying the objects and moving them from one region to another. What does he mean by sweeping out? I don't know what this means. I hope we will find out in further articles. Experiment. Can we see it in action? Of course we can. What we want is to start lots of threads, what would claim some TLAB of their own, and one loner thread what will exhaust the Java heap, crushing with out-of-memory exception, which we will use as the trigger for a heap dump. And workload looks like this is fine. He is taking like imports, yeah, so main final tractorist of equals 300, yeah, in Russian there is some anagram with not anagram but some funny like joke about 300 tractoristov. Countdown latch CDL actually countdown latch for 300 in this case, yeah, and he starts iterating and it says like allocate and wait. So what is here? Yeah, so he is creating the object, reducing countdown latch, yeah, and put them to sleep, yeah, for some time, and of course he's using object somewhere so that it is not optimized, yeah, and doesn't remove this object allocation. So when countdown latch will will await, it actually will create 300 threads, and this one allocate and die, it's just a single thread here, it starts here, yeah, and it starts to add new to new object to the collections to exhaust the heap. So in order to get predictable TLAB sizes, he is using this epsilon GC, yeah, and 1 gigabyte of heap. So he unlocks experimental options in order to use epsilon GC and take heap dump on out of memory error, and it quickly falls and produces the heap dump for us. Opening this heap dump in Eclipse Memory Analyzer, I like that tool a lot. We can see this class histogram, and you see that the biggest allocation, not by the number but size, is the int arrays. Yeah, so there are a lot of objects as well, but they are small because they are empty. This is these objects which are just created in the loop. See how int arrays dominating heap consumer. There are these are our filler objects. Granted, this experiment has a few caveats, and my comment here is it's very I'm not sure. I can, like, someone can argue maybe, but creating int array as filler object, what will be the consequence if we have a lot of int arrays in our application, yeah, and how to define if those int arrays are filler objects or they are real objects which are really used by our application. That's kind of question mark. First, we configured epsilon to have static TLAB sizes. A high-performance collector would instead make the adaptive TLAB sizes decisions. So he explains the experiment. So basically, that TLAB sizes will be different if we don't use epsilon, which would minimize the heap slack when a thread had allocated a few objects but still sits on troves of TLAB memory. This is one of the reasons why you don't want to issue large TLABs without thinking twice. Yeah, so what he's saying is that TLAB sizes should not be of too big size, because otherwise we will, because in this case we will have a lot of filler objects. Still, it is possible to observe filler objects when an actively allocating thread has large TLAB issued to it, and it is only halfway there in filling it up with real data. Second, we have configured MAT, what is this, to show us unreachable objects. MAT, this Eclipse Memory Analyzer, okay. He configured it, yeah. These filler objects are by definition unreachable. Their presence in the heap dumps is just a side effect of heap dumping using heap parsability property to walk the heap. These objects do not really exist, and a good heap dump analyzer tool will happily filter them out for you. Here is the answer for the question. Yeah, well, if we are using good heap analyzer, it will filter out those objects and we will not see them in the real heap dumps, and this is the way how we will work properly with interarrays which our application will create. This might be one of the reasons why crushing 1 GB heap dump has only, say, 900 megabytes worth of objects in it. Observations. Having TLABs is fun, having heap parsability is fun too. Combining both is even funnier and sometimes leaks out internal trickery. If you see surprising behavior from any runtime, you might be looking at some clever trick. This is the end, so maybe now we understand a little bit more about TLAB. Now switching to the talk, yeah. By Yonut, Java Performance Techniques, the cost of hotspot runtime optimizations. Let's start.
So, hello everybody and welcome to Java Performance Optimizations talk. Today we are going to discuss about some of the optimizations that happens during the runtime inside the hotspot in particular, but all the things that we discuss in here are also valid for the OpenJDK because it's mainly the same source code. My name is Ionuț Baloșin. I'm currently a software architect for Luxoft. Overall 10 plus years of software development experience, in particular very keen on performance and tuning topics, plus software architecture. I'm as well the technical trainer inside the training department in Luxoft, and as well conference speaker. From time to time I write some articles on the performance and software architecture. Our agenda for today, it's a bit, contains a lot of topics. We'll start with just-in-time a briefing introduction about what means the JIT, and after that we'll go through a few optimizations, starting with uncommon traps, null sanity checks, and we'll see what's happened during the runtime in regards to this optimization. So how JIT behaves to benefit of the best optimizations. What's in for you to take away out of this talk? It's a better understanding about what happens inside the hotspot virtual machine from the just-in-time compiler standpoint. As well, you will learn few just-in-time compiler techniques, how JIT triggers those optimizations. And at the end, we'll go through some cases when just-in-time compiler it's not able to compile anymore the code. So we will see some corner cases which prevent the just-in-time compiler to optimize our code. In a nutshell, it will be useful for you if you want to tune to squeeze the ultimate performance out of your Java application. Few things about my configuration, because during this talk we'll study a lot of we'll go through a lot of tests. So a few things about my hardware configuration. I was using i7 Skylake processor with 16 gig of RAM. From the software perspective, all of the tests were done on Ubuntu, but of course I used as well Windows just for the sake of this presentation. The JDK was the last one, the last official one, 1.80, update 1.1, and I was using a JITWatch tool and HPJ meter just to prepare the talk. Okay, so a few things about just-in-time compiler. It's a very brief introduction just to put a bit the context. What we have during the runtime, it's mainly the JVM with the execution engine. The execution engine made of the interpreter and just-in-time compiler. Of course, there is a class loader, garbage collector, but it's not our interest for today. We were mainly focused on the just-in-time compiler for today. Just-in-time compiler, if we have to zoom in a bit, it's made of the client, the C1 compiler, which triggers only rock-solid optimizations based on the invocation threshold, which is around 1.5k iterations, so it's around 1,500 iterations. The second one is the server one, which does better optimizations in regards with C1, but it needs a higher threshold, so it's around 10k iterations to trigger and to compile the code. And as well we have a tiered mode, which is a mixture between C1 plus C2, and it has a lot of tiers. It starts in interpreter.
Sorry, this is previous time. We were like doing running the code with print compiler, print compilations, yeah, flag. And we have seen this tier 3 and tier 4, yeah. So client server, this is something that we have seen, yeah, that this tier 3, tier. And actually here he is showing that tier 1 and tier 2, which we were not able to observe during our test. This is C1 without profiling and C1 with basic profiling. Yeah, so that's something that we have tried previous stream. Yeah.
It goes in C1 without profiling, with basic profiling, with full profiling, and it reaches the second one. If we have to take a look over the speed, of course, in the interpreter, we have the lowest performance speed out of the Java code that we wrote initially, because mainly the bytecode is interpreted. The second level, I would say, is the C1. In the C1, we might have around 5 times speed improvement in comparison with the interpreter, and the best one is the C2. In some cases, it might reach like 100 of times more than the interpreter. But of course, it does a lot of assumptions. It as well do a lot of the optimizations, so it needs more context. By context, I mean more number of iterations. All of this being said, just a bit of context, let's dig into the optimizations one by one to see what's happening under the hood and what just-in-time compiler does in order to do that. Just as a remark, during the next optimizations we'll take a look over the Java code and the assembly code. Why? Because the assembly code, it's more interesting. Based on the assembly code, we will figure out what's really happening under the hood, and for us to have a better understanding about these optimizations, we definitely need to understand the native code. We will skip for this talk the bytecode. Okay, the first optimization or technique, I would say it's more a technique, it's called uncommon trap. What's an uncommon trap? It's mainly a situation which is unlikely to happen inside during the runtime inside the hotspot, which means that just-in-time compiler treats it as a check. If this check is happening, it bails back into the interpreter. This is mainly an uncommon trap. It's mainly a situation unlikely to happen, but when it happens, the just-in-time compiler bails back into the interpreter. To understand it better, let's see this very trivial example. What I did here, I created a loop. Inside that loop, I iterate through the loop 20k times, yes. And inside the loop, I call a hot method all the times with true. The hot method, it's like in here, it receives the boolean, and based on it, if it is true, it returns 1. Otherwise, it returns true, and returns the counter. Why I chose here 20k iterations? Because I wanted to be sure it reaches the C2, the second level, and as well to benefit out of the best optimizations during the runtime. And I took out this code and I launched my JVM in here with print assembly. Print assembly says for the JVM I want to print my assembly during the runtime. And of course, I want to print the assembly in the Intel syntax. There is as well AT&T syntax, but for me, I more use the Intel. It's mainly the same, but it's just a matter of representation. And I disabled the tier compilation, which means in our context, I was using only C2. I don't want to go through the C1 compiler. I want to reach directly the C2. I'm not interested in all the intermediate optimizations, only in the final ones. And of course, the last one, it's my class. And if we scroll and zoom it a bit into the assembly code, of course, I really simplified for this talk just to be easier to be understandable. What we have here, we have the hot method, which receives my boolean. It's this RDX. It compares the RDX with 1. If it is not equal, we see here it does a jump. But if it is equal, it returns true, which means if my method receives 1, returns true. But if it is not the boolean, it is false, it does a jump. And this is the jump to an uncommon trap. What's an uncommon trap and how it works? Because I called my method during the runtime only with true. The hot method was called only with true for 20k times. The just-in-time compiler assumed that there is an unlikely situation to be called with false, and just-in-time compiler added an uncommon trap. And uncommon trap is mainly a call to this address. When it happens, just-in-time compiler locks the method, marks as not being entrant, and switches back in the interpreter. So based on this, we can see that JIT, just-in-time compiler, optimized at the moment only for the true branch. And for the false branch inside the code, it put this uncommon trap. If we get back to our initial snapshot of the code, we see that we have the hot method called only with true. It got optimized, it got compiled, and if we have to measure just one iteration after it reached the C2, on my laptop at least, it took around 300 nanoseconds. But the question is, what if I call my hot method it false just immediately after? Calling the method with false just immediately after and measuring the time elapsed, we see that one iteration took like 100 times more than the previous one. And it leads me to the question why. What happened under the hood inside the JVM from the just-in-time compiler perspective to have such big difference between these two calls? Just two calls in a sequence. To spot out what happened, we have to redo the test. Relaunch the test mainly, and this time I was using print compilation because I'm interested in all the things that happens under the hood. I want to see what was compiled, what was disabled for the moment. And if we check the output for the hot method in here, we see these two lines. But what it means, because apart the trivial methods, we see a lot of other information. The first column corresponds to a timestamp. It's mainly the number of milliseconds since the JVM has started. The second one, it's mainly a compilation ID for the just-in-time compiler. The third one, that percentage, it stands for on-stack replacement. What's on-stack replacement? For example, if you have a method and inside that method you have a long-running loop, that long-running loop could trigger the compilation for that method. This context is the context of on-stack replacement. What happens during the runtime, the stack frame, it's replaced by a native stack frame on the stack. Another thing is this around 4, which is mainly the bytecode index which triggered the on-stack replacement. So it corresponds to this percentage and the number of bytes that got compiled. Okay, so getting back to our
previous time, if you remember, when we were looking at the compilations from IntelliJ, yeah, I told that I don't know what it is, and now it's clear. Yeah, it's not the line in the code, but it's number of index in the bytecode. Yeah, so this is the line in bytecode which triggered this OSR compilation. Another thing which I wanted to mention here is that this uncommon trap sounds very close to another optimization. I'm not sure if it is the same or this is just uncommon traps is common term for JIT and Java. What is called branch prediction. Yeah, so I guess this is like very common for compilers. Yeah, maybe this is like low-level call, but what is branch prediction? Yeah, so he predicts, for example, if we have like if statement, and it's like 5,000 times it was evaluated to true, it automatically compiles the code in a manner that it will go to the same branch. And only after like it's evaluated to false, yeah, it will need to like decompile back. The very good analogy which someone, I don't remember who was explaining that, is they told about like all-time trains. Yeah, so like imagine like, I don't know, beginning of 20th century, the trains were not with radio, etc., and all like switching the train line was made manually, and the trains needed like how it worked. Yeah, so the guy is going and there is a train goes to like these rails go to 2 different directions, and he needed to stop the train, then go out, manually switch the track, and the train would go to right direction. And now let's imagine that this guy on the train, like stopping and starting the train is kind of very difficult process. Yeah, it's like it will consume a lot of coal or whatever. So he was like, and he was going by this track like by the same route, same schedule for like 100 times before, and every time the train was going to the right direction where he needs it. Yeah, so he decided at some point that, okay, I will not stop the train, I will not go out, I will see where the train will go. Yeah, and if it will go to the right direction, I'm just continue going. But there's a chance that this time something has changed, yeah, and he will go to wrong direction. So he is just standing and watching, yeah, not without stopping the train. And if occasionally the train will go to the different direction, then he needs to stop it, then go back, yeah, switch like back gear, I don't know, whatever it was used in these old trains. The train goes back all the way, yeah, then he goes out from the train, switch the track and go to the right track. Yeah, so it's much more time consuming but the probability of such event is very low. And that's why it's like beneficial not to stop the train before this like split. It looks very similar to what he's describing by these uncommon traps.
Our scenario after this explanation, we can see that when we trigger the method with true, it became compiled. The hot method initially became compiled, and because and as well inlined, and because we have a long running loop inside our main method, the main method itself was compiled, and this compilation was triggered from the on-stack replacement perspective. What happened afterwards immediately when we called just once with hot method of false, we see here this mark which is saying not made not entrant, which means all the assumptions, all the optimizations made previously when the method was called by true are not valid anymore. So mainly the uncommon trap was hit and the method was bailing back into the interpreter. That's why there is that big discrepancy, like 100 times more when I called once with false in regards with the previous one. If we have to illustrate a bit from the thread's perspective what's happening during the runtime, initially we had our hot method while starting in interpreter. After a certain number of iterations, the C2 compilation level was reached. The method was compiled, but when we called with false parameter, we hit the uncommon trap, which means at the runtime we bailed back into the interpreter. That's why we had that big discrepancy between the time elapsed. The question is, what happens, for example, if there are other threads running the same version of my hot method? The answer is that if the other threads run in the same time the same version which was compiled, and if they don't reach the uncommon trap, they continue the execution. But if I have another thread like in here which calls my hot method afterwards, after one of the threads reach the uncommon trap, it starts from the interpreter from the very beginning. So this is the explanation what's happening during the runtime. Now what I did, I continued my experiment and I optimized with true and false. I also included hot method of false into a long running loop, and I checked the compilation. And in here what we have, it's the first two lines are very similar to the previous one, which means we had the hot method, it was compiled. We have here an on-stack replacement for the main method, so the entire main method was compiled. And when we triggered the hot method just once with false, it became not entrant, but because we have this long running loop in here, it became again optimized, and it was compiled, and as well it triggered again the compilation for the main method. So as you can see, during the runtime, if you are using the C2, there are a lot of optimizations. The optimizations, just-in-time compiler, it's eager to do a lot of assumptions just to make the better optimizations for our code. Going further, if we have to take a look over the assembly, if I have to run with print assembly as we did before, we see here in this case we have this C conditional conditional move not equal, which means in this case after we hit the uncommon trap, the just-in-time compiler falls back to the traditional way of handling these checks. So if the just-in-time compiler has the context of being able to reach both branches, branches for true and branch for false, it doesn't do any more uncommon trap, and it switches back to the common way of handling this, using mainly jump instructions. That's about the uncommon traps. Some sort of summary for you. So if a conditional statement was following only by a single branch, an uncommon trap, it's a good idea to optimize this during the runtime, as we saw. The thing is that once the uncommon trap it's hit, the just-in-time compiler have more context. So in this case, it doesn't do any more uncommon traps. And just to summarize, the uncommon traps, they are a good solution to optimize the code during the runtime. But since they are hit while they are while the thread it's hitting the uncommon trap, it's costly. It's costly because it has to deoptimize, it has to bail back into the interpreter and starts the execution in that interpreter. Inside the hotspot, there are a lot of uncommon traps situations, and for this talk, I took out of them the null checks. How hotspot handles the null checks. For this, I took this code, again, the hot method, the same method, and I'm calling with an integer which is not null. And inside the hot method, I say if my integer is not null, multiply and return the result, otherwise return 0. So I have this null check. What we have during the runtime? During the runtime, again, I started my program. When the JVM was triggered, I set print assembly because I wanted to check how it behaves from the native code perspective. And as we can see here, the assembly code is very, very simple. It has mainly, after I clean it a bit, it has this move and this EAX multiplied, this byte operations. Bit operation, sorry, which means mainly put the value from the integer in EAX and does the multiplication by 2. There is no null check explicitly added in the assembly code. Why? Because as we can see here, there is an implicit dispatch to this address in case there is something wrong. What could be wrong? It's mainly a segmentation fault. Imagine the C or C++. What's happened when you call something which is null? You got a segmentation fault. It's implicitly handled by the hardware. And in this case, once the segmentation fault is in here, we have a null handler for our uncommon trap, and again it bails back into the interpreter and starts from there. So in this case of handling nulls inside the code, there are no explicit checks. Instead, the just-in-time compiler leverages on default OS signals, segmentation faults, for example. When a segmentation fault is happening, it is caught by the OS, it is handled by the JVM, and inside the JVM, it is, for example, there is a decision if null pointer exception is thrown for the programmer, or if it is not the case, as we see here, because we have an explicit null check in our code, it bails back to an interpreter and starts the execution. If we
Okay, just a small remark to remind a little bit what we were doing at the beginning. You remember we were watching the default threads, which JVM starts from the beginning, yeah, and there is a thread which is called signal dispatcher, yeah, and this signal dispatcher is actually listening to the signals from operating systems and somehow reacts on them. Yeah, so it works all the time. Like when we start JVM, signal dispatcher is started, and as Jonut saying is that looks like for null checks in the beginning. There is no explicit null check, yeah, in the assembly code. It's just signal dispatcher is listening to this segfault signal, and when it receives it, yeah, it's throwing null pointer. But how it's managing, like, segfault can go from different places. Yeah, I guess signal dispatcher somehow knows from where it is coming and by what it was caused. Yeah, and then he will be throwing like null pointer exception.
We have to optimize a bit more, so we call the method with null, and after that immediately 20k times with a value which is not null, and we have to print as well the assembly. We see here the test, it's explicitly added. What it's in here, mainly we test this RDX, which is the parameter our integer received. If it is null, there is a jump in here for L001 label, and in here it's a XOR between the same register, which means return 0 basically. And we have a jump to another label, which is the return of our method. But if it is not null, it's the same code as we did previously when the null was implicitly dispatched to that address. So this is the way of relying by default on signals inside the JVM, particularly for this case of dispatching or of handling mainly the null checks inside the JVM. But after the moment that our code reached the null, there is no any more uncommon trap, as we see here. It's an explicit check. Just to sum up, null checks relying on signals are natively handled by hardware and as well by OS, and very well handled by the JVM. But in case they are triggered, of course, it's costly. It's costly because you have to pay the cost of catching the signal, the segmentation fault signal, handling it, bailing back into the interpreter, and continuing the execution. And as a conclusion, don't let null happening a lot in your application, because especially the first time you will have a lot of segmentation fault signals triggering under the hood, and after that, after these segmentation faults are triggered, the code is recompiled by this time with jump instructions. So there inside the code there is those test conditions, which might be costly as well. Another kind of optimization, it's called devirtualization. What's the virtualization? It's mainly a technique to turn polymorphic calls into direct calls. What it means, for example. On the right side, we have a parent class, which is called CMAT, which has a method compute, which receives an int, and it is extended by ELG1. This ELG1 is the first implementation. It's mainly an extension of this parent class. And if we have to test it, I put this in a long-running loop, and inside the long-running loop I call the hot method in here, and inside the hot method I say mat.compute. And what it does internally, mat.compute, it returns the I multiplied by a constant. So very basic implementation. And afterwards, I started my program again with print assembly, because I was curious what's happening, how just-in-time compiler handles these virtual calls, because mainly it's a virtual call, it's a polymorphic call. And if we zoom it inside the assembly, we see
I was saying about this in one of the streams, I don't remember which one exactly, but that call to a direct implementation, for example, if he was calling compute directly on ALG1, yeah, on this class, its bytecode instruction is invoke, and when we are calling it on interface, or like here he is saying like even on base class, it is invoke virtual. So it's a little bit different bytecode instruction, and this is what he means by like virtualization and devirtualization.
Just-in-time compiler handles this these virtual calls, because mainly it's a virtual call, it's a polymorphic call. And if we zoom it inside the assembly, we see very simple things. Here it's mainly the first line, it's mainly a conversion, and on the second line it's mainly the multiplication. So it just receives something, it does the conversion to double precision, and afterwards it does the multiplication, and it puts the value inside this register, and it is returned back afterwards. As we can see, there is no check if my instance during the runtime is of type ELG1. So, which leads me to the conclusion that this case of polymorphic calls, if they have just one single target, which means single target monomorphic calls, they are inlined, and the just-in-time compiler doesn't add any uncommon trap for them. Let's see, if we go further, what we have in case we add the second implementation, and as well we enrich our test by this instance, and this instance calls the same hot method in the loop, running loop. If we check the native code, it's a bit more complex. A lot complex, I mean more instructions added, and in this case of two possible targets invocation, just-in-time compiler adds explicitly the check. What it does, for example, it checks if the instance is of type ELG1, which is in this compare. If it is of type L1, it jumps in here and it does the multiplication. After that, if it is not the case, it compares with ELG2, if it is an instance of ELG2, and if it is not the case, it jumps in here and it triggers the uncommon trap. So mainly, if there is an instance of not ELG1, neither ELG2, I have to trigger the uncommon trap. But getting back, if the instance is of type ELG1, it does as well this multiplication. So mainly in this case of bimorphic calls, two target calls during the runtime, there was inlining which was occurred, so the just-in-time compiler did the inlining and as well added an uncommon trap for the possible third or fourth extension of my parent class. Let's see now, let's go further with this, and let's see what happens if we extend with the third implementation, the same base class, and as well we enrich our test, and we call the test with a hot method with ELG3 and I. In this case, if we print the assembly, it's very, very simple. It's simple because it contains just a virtual call to the hot method, which leads me to the conclusion that the megamorphic calls are mainly the calls starting with the third implementation. The just-in-time compiler neither inline nor do any uncommon trap. It just does a virtual call, which is even more costly than in case of bimorphic calls and monomorphic calls. If we have to reiterate on it, monomorphic calls are inlined without any uncommon trap. Bimorphic calls are as well inlined as we saw, but there is an uncommon trap added in the code. The just-in-time compiler adds a check. If the instance is not of type ELG1, neither ELG2, I trigger the uncommon trap. And megamorphic calls are handled as virtual calls. The just-in-time compiler doesn't do any optimization. It just triggers the virtual calls. In reality, what's the cost from, for example, from one monomorphic to megamorphic call? It's around several nanoseconds. I would say during my test, I spot it out as being like 3-5 nanoseconds. So anyway, it's very performant in any case, but you should have this this idea in mind that once you reach the third and the fourth and the sixth implementation, it becomes more costly because it has to resolve the virtual calls during the runtime or upon each method call. The next one is called loop unrolling. What's loop unrolling? It's mainly a technique to reduce the number of jump instructions if we have long-running loops. For example, what we have in here, we have a method, and inside my method I compute the sum of this array. And at the end I return the sum of the array. If I have to compile and see the print and see the assembly, as we see, there are a lot of additions. A lot of additions inside this loop. It's from here to here, and the counter increases by 8 mainly, which leads me to the conclusion that the just-in-time compiler did a loop unrolling, and it unrolled the loop by 8 iterations in the same time. This is a very powerful technique because, for example, in case you don't have data dependency between all of these addition statements, there might be parallelized and run in parallel. And another important thing is that, as you see in here, it starts from 1. Even if my initial sample case at the Java code level, I started from 0, which is another technique. It's called loop peeling. So what mainly does the just-in-time compiler during the runtime, it peels out of the loop only the first iteration to do some checks. For example, it could be useful as well for memory alignment, and putting aside the first loop iteration, it iterates and parallelizes the number of additions. And as well in here at the bottom, if there is some remaining, for example, if my array it's not multiple of 8, it triggers here the remaining out of that list. Which and if I have to put it into pseudocode, it looks like this. The loop peeling, it's the first iteration, and from the counter of 1, it does 8 additions in parallel. And here at the bottom, it triggers it handles the remaining of the sum operations. Which leads me to the question for you, because we are aware, we have in mind this sort of loop unrolling technique. Would it be useful for us to be a bit smarter in advance? For example, having an array and instead of iterating one by one to do the sum, to put like four additions in the same loop iteration. What do you think? Would be a good idea?
No idea. I don't know. There is someone saying something in the background.
Any other guesses?
We didn't hear even this one.
It could do better. Yeah, so thanks. Let's see how it does. How the just-in-time compiler deals with this some sort of eager optimization in advance from the programmer perspective. I don't print again the assembly because it's a bit more complicated. I try to translate it into pseudocode just to be easier for us to understand. And the assembly code look like this. It did as well the loop peeling, so it peels the first iteration, which means the first 4 additions. So starting from fourth one, it did the same. So what it did, it mainly reloop what I did because it thought it's not a very efficient way of doing loop unrolling, and it did loop unrolling in a more efficient way that I did in the beginning. So which means mainly it reloop my loops and it unroll them again. So at the end, in this, we end up with the certain number, the same number, sorry, of iterations. But just to tell you that the assembly code, it's much more complicated. So we try a bit to put the just-in-time compiler into difficulties, which leads me to the conclusion that it's not quite a good idea to do this kind of optimization in advance. So let the just-in-time compiler do them for you, because just-in-time compiler knows better than us during the runtime, especially for this case, for the loop unrolling. Loop unrolling as well, just to sum up, it's a good technique because it reduces the number of branches and as well the number of jump instructions, and also opens the door for instruction level parallelism, which might allow basic block level vectorization optimization. And as we discussed, avoid this manual loop unrolling, because let the just-in-time compiler do them by itself, because he knows better than us what's in compliance with the hardware platform, to your CPU, to the number of cores, to the number of threads, how to do it better, in a better way. String deduplication, it's the next optimization that happens during the runtime, which mainly says that if I have the garbage 1 enabled and starting with Java 1.8 update 20, during the runtime, during a GC cycle, the garbage collector searches for strings backed by the same char arrays. And how it searches, those char arrays, the strings, sorry, should have the same hash code and the same char array. And if there are some similarities, if there are strings that are backed, all the redundant char arrays are removed. In this case, it optimizes the memory footprint during the runtime. Having this sort of explanation in mind, I did some tests on my machine, and what I did in here, I created a very simple application. I created a lot of strings, simple application. It optimized.
Just a reminder, yeah. I guess you guys all know it, but in case not, if we are creating the strings with new keyword, yeah, it will not be automatically put in the pool. Which means that every string will have a separate remember, yeah, if we will create string str1 equals voxed, yeah, and without new keyword, just this literal, it will be created and immediately put in the string pool. And next time, if we will create string str2 equals voxed without new string, it will actually not create a new string, because voxed is already in the pool and it will reuse it. So the equal sign between these two strings, str1 equal to str2 will be true, and equals method will return true. But in this scenario, yeah, str1 with double equals will give false, because this is new string and new string, which means they will have two different references, but equals method will give true as well. But as we see, what he is saying is that this deduplication, that basically we have two different references, but they are pointing to the same char array which is inside, yeah.
Optimizes the memory footprint during the runtime. Having this sort of explanation in mind, I did some tests on my machine, and what I did in here, I created a very simple application. I created a lot of strings, and I set a threshold for my heap memory to 1 gig. And because I wanted to benefit out of the string deduplication optimization technique, I as well explicitly set the G1. G1 is not enabled by default in 1.8. And I did 2 types of tests. The first test was with string deduplication, and the second one was without string deduplication, as you can see here. So what we had from the stop the world pauses, in case...
So the red one is with plus, it's with use string deduplication, and the blue one is without, yeah, because I see the quality is not very good here and it's not very visible. So the blue one is without string deduplication.
In case of string deduplication, the red one, we see a bigger number. So the number of stop the world pauses took more. Stop the world pause took more. Why? Because after a certain number of GC cycles, the G1 collector had a bit of work to do in comparison with the blue scenario where I deactivated the string deduplication. So it had the work to do of finding the strings and removing the redundant char arrays from the main memory, from the heap mainly. So in this case of context, we say that string deduplication may add, not may add, it adds definitely longer stop the world pauses during the runtime. But it is also beneficial, and in my case it was beneficial because if we get back to this bounded amount of memory, in case we use string deduplication, the memory was was reclaimed during the runtime, and I was able, my application ran for a certain number of cycles more because I had more heap to allocate more strings in comparison with the previous case when I gotten out of memory earlier. Why? Because in the heap memory I had a lot of redundant char arrays. So it's useful in this case. And if I have to take a look as well over the heap memory usage, I see in here, without string deduplication, I see here the heap usage after a GC cycle was bigger than the heap in case of using string deduplication. Just to sum up, string deduplication reduces mainly the memory footprint. It's a good technique. It was added in the JVM just for this, to reduce the amount of heap, and it's very useful in case you deal with bounded amount of heap during the runtime. But it impacts performance. It impacts performance as we saw the stop the world pauses take more, of course, because G1 has additional work to do in regards with reclaiming the char arrays. Biased locking. Biased locking, it's in there since 1.6, which says biased locking, it's a technique in case of uncontented locks. For example, I have a synchronized method, but during the runtime I have just one thread that calls it. There is an optimization which avoids the penalty of the real synchronization. This penalty of real synchronization relies on OS mutexes, conditional variables, signals under the hood, so a lot of stuff under the hood that it's triggered by this synchronization on locks. And the technique says don't go real synchronization, just bias the lock towards the thread it owns it. I did as well some tests to check if this biased locking scheme impacts performance. In my case, what I created like 50 threads. Inside each thread, I put a synchronized on the shared instance, and each thread locking on the same shared instance, incremented a counter. I started my threads in here and I joined for all of them. And if I started my JVM with bias locking startup delay 0, why is that? Because by default bias locking scheme it's active after I think 4 seconds, so it's not activated, it's not enabled from the very beginning. So I started my JVM with 0 because I want from the very beginning, just for the sake of my tests. And I printed the application's stop the word pauses. And as we can see, the GC output, it's a bit verbose. It contains a lot of total time for each application threads were stopped. So a lot of them. I did a sum. And in my case, it's around 1 millisecond. Which means this millisecond was mainly spent in operations like revoke bias and enable bias locking. So we pay a lot during the runtime, 1 millisecond, mainly for this bias locking mechanism. I did the same test again, but this time I disabled bias locking. I disabled it from the very beginning, and here the output is more clear without any stop the word pause, so around 0 seconds approximately. So 0 seconds, which leads me to the conclusion that bias locking, it's a good technique. It helps you a lot in cases where you don't have contention. But if you have contention, you pay a lot the cost of the stop the word pauses. So that's why mainly a recommendation for you, if in your application you have to deal with a lot of threads, there is contention, maybe it would be better to disable the bias locking scheme, because you have to wait for the stop the word pauses during the runtime. Another technique, it's mainly the inlining, and today we are going to check, to study the concurrency implications in regards with the inlining. What's the inlining good for? The first answer, it will be it saves us from the pop and push overhead, but it's just, let's say, I would say very naive explanation. It's not like that. In reality, there are a lot of benefits. The first one is about the consistent control flow of the code. If just-in-time compiler sees that the code is consistent, the flow of the code is consistent, it relies to move it around and deals with optimizations. It deals a lot with optimizations across boundaries. For example, caller and the callee. If the caller and the callee can be inlined together inside the big piece of code, it does optimizations. And as well, if we can inline something, in some cases it saves the number of memory loads. And immediately we'll see what means this kind of technique. To dig in inside it, first a bit of context about the test scenario. Again, the same long-running loop, but this time inside my hot method, I called hate method twice and with method twice. So it's mainly a call to reference a variable out of the memory, let's say, and store it in these locals. And at the end, my method did some multiplication and addition and returns the result. What we have in here, because between these calls on the height and on the width methods, we explicitly call in between a method which can't be inlined anymore. What means can't be inlined? A method that just-in-time compiler cannot inline, so the caller can inline the callee body. In my case, how it looks like, it's a bit funny, because I created it in an explicit way to prevent the inlining from the gist perspective. So it means, for example, it calls M2, M3, M4 up to M11, which at the end it returns 0. Why I did that? Because implicitly the hotspot JVM has the parameter which says max inline level its default 9. So after the 9th level of call depth, just-in-time compiler is not able to inline our code anymore. Having this said, if we get back and we run our example and check the assembly, what's in here, we see the explicit call for the height method to retrieve the value. We see this virtual call to the method which can't be inlined, and again the same call to the height method. And if we continue zooming into the assembly, it repeats the same call to the same method which can't be inlined, and twice, 2 calls mainly the width value, twice width values out of the main memory. Why is that? Putting it into a bit of generic context, if we have 2 memory retrieval, but in between we have a method that just-in-time compiler can't inline that method, the just-in-time compiler assumes that there might be other threads that change the memory. So it explicitly forces a new reload from the main memory from this height value. That's why we have twice calls for the height and twice call for the width. If we repeat the test and we increase the default max inline level just to be able to inline that method, we see the native code. It's like in here. It does only once the retrieval from the height memory and just once the retrieval from the width, and as well the memory the method can't be inlined was inlined. So this is a very, very interesting technique to keep in mind, because if we deal with methods that can't be inlined, you prevent a number of other optimizations. So for you to check inside the code, it's mainly based on the size. There are methods that if they are bigger than 35 bytes, they are not inlined, even if they are called more than 250 times. And in case you have so in case you have frequent methods, for example hot methods, those methods are not inlined anymore if they are bigger than 325 bytes. So be careful with this, because you prevent inlining. So preventing the inlining, you prevent any other optimizations during the runtime. As well, the max inline level, the call depth level that we discussed about, it's 9 by default, and there is a max recursive inline level for recursive calls, which is set to 1 by default.
To be honest, in all literature and talks which I have seen usage and changing only one option. It was this max inline level, so it's like the depth of the calls. So one method call another, then this one call another, etc., etc. So default is 9. I guess this is pretty much enough for clean code. If it's some kind of deep call stack, it can be increased. I don't know why such defaults are taken. No idea. In general, from what I understood, you should not change these parameters without real need, and you know why you are doing that. So if you see that in your code you have a lot of them, then maybe there is a sense. But usually what Alexei is writing on his page, that if everything works, just don't touch the defaults.
How to check in your code? Just a very straightforward technique. There is a jar called jar scan, so you can check out of the code base on your side which methods are not eligible to be inlined. because their size is greater than 325 bytes. So it's a very straightforward technique that recommends you what to refactor out of your code in order to allow inlining to happen during the runtime. And the last part of the talk, it's in regards with methods that don't JIT. The first case of such method, it's a method which has a huge body. By huge body, in this case, it's a body that has 805 bytes. So for this case of methods, of course, the example is a bit exaggerated just to prove they are not compiled. And if we have to run this and as well to print the compilation, as we see here, there is nothing which got compiled during the runtime in regards to the hot method, only the main method. If we have to check inside the JIT watch tool, we see written in here no JIT compiled. That's why. Why is that? Because there is a flag inside the machine which says don't compile huge methods, which is enabled implicitly to true. But what is a huge method? A huge method, there is as well a task for the OpenJDK. A huge method, it's mainly a method that has more than 8,000 bytes. So in this case, they disabled implicitly their compilation because as it is written here, they are not well tested, and probably they'll have more other implication in regards with the code cache, to the fashing policy on the code cache. So if you have such huge methods, it's better maybe to refactor them, because turning off don't compile huge methods might cause any other side effects. The next corner case of method which are not compiled anymore are methods with a lot of arguments. In here we have methods, for example, with 70 doubles, very, very big signature. And the return is very simple. It returns the sum of all. In this case, if we have to compile, with the just-in-time compiler prints this kind of warnings saying that unsupported incoming calling sequence or unsupported calling sequence. If we search on the web, there is also a task for the OpenJDK. It's still in open. I think it's there since the very early version, the 6th one. It's moved towards 10, so probably there is a rumored improvement on their side in regards to these methods. So all of this being said, I want in closing to end up with a quote from Richard Feynman, which is a guy which really inspired me. It's a very, very smart, was mainly very smart guy, and he said that it doesn't make a difference how beautiful your guess is, how smart you are, who made that guess. If it disagrees with the experiment, it's wrong, it's nothing. That's why during this talk I studied from the very high level, from the Java code till down to the native code, mainly to understand what's happening under the hood and to prove the optimizations. Otherwise, if we don't have a good experiment, it's still a guess. And my advice for you is always to be curious, to experience new things. Only being curious, only searching under the hood, you will understand the things in a better way. Thank you very much.
Thank you very much, Yonut, and let me switch to the full size. So that's the end. Thank you very much, guys, for watching. What I have noticed for myself, yeah, it was very tough, I would say. Especially it was hard to follow the assembly code, which he was like, I guess he was showing during the talk with the pointer, some things which we didn't see, of course. But still, we've got a lot from it. What I have noticed, I thought that it's only me who is always saying when we are speaking about this performance tuning stuff that probably and mainly and everything, I guess, works perfectly with experiments. Yeah, because a lot of things on my level, for example, yet are not very precise. So it's not a kind of science which is like 2 plus 2 and we know that it is 4. So everything should be confirmed with experiments, and mainly we should get good results. Guys, thank you very much for watching, and I hope to see you again next time, next Thursday. Thank you and have a good night. Bye.